All right, today we're going to take a look at section 7.7. Okay, the main idea, it's the second part of the title, are natural logarithms. In 7.6, we took a look at a special kind of logarithm, one with a base of e, or sorry, base of 10. We get to a base of e today. Base of 10 in 7.6. And that one probably hopefully maybe makes some sense why 10 is a common enough base to get its own log. Today, we talk about another special log. It's the log with the base of e. Now, that may not seem significant to you because you probably don't yet know what the number e is. But a log with a base of e is another special log that has its own name. We call it a natural log, but we symbolize it with the letters ln. Seems like it should be NL since it's natural log, but we go ln. It's not a 1, that's not an I, it's an L. ln stands for natural log. We do not bother writing the base number because when we write ln, we understand that means it's a base of e. So what is the number e? Well, e is an irrational number. We know some other irrational numbers. What are some irrational numbers? Pi. Pi is an irrational number that we symbolize with a Greek letter. E is, and the natural base e is another irrational number that we symbolize, but with one of our letters this time is e. Some other irrational numbers would be like square root of 2, square root of 5, those sort of things. So e is a decimal that goes on forever and never repeats. But the first several digits, 2.71828, etc. E does have some uses. We'll talk about it in the context of finances. Definitely have some uses there. At least there's some others as well, but that's where we're going to kind of take a look at it, is in finances when we talk about compounding interest again. But before we get into that, I would encourage you to have out a graphing calculator. I guess your own calculator would probably work as well if you have one, but grab a calculator of some sort, and then we can get rolling. So we'll start off with ln of 7, or the natural log of 7. So what it means is the number e, if we raise it to an exponent, a certain exponent, we will get an answer of 7. What is that exponent? That's what ln of 7 will give us. We can just type in on the calculator ln 7. Last time we used the log button. Now, right by that log button, you should see a button that says ln. Probably right below it if you're using a graphing calculator. So you can just type in ln 7, you get your answer. So it's about, we'll go to 4 decimal places again like the last section, 1.9459. Now, a natural log is the inverse of exponential with a base of e, so we can also, while we're at it, plug in the calculator. Let's try using a power of e on the calculator. Let's go e to the -3. Let's find out what that is. I would point out to you, if you look at the ln button, right above it in blue, so the second ln is your e to the x button. So hit second ln, gives you the e, type in your exponent of -3 and get your answer. So if you use the subtraction button instead of the negative button, if you do e to the -3, that would probably give you an issue. So make sure you use the negative. If you have any problem, I would verify that first. There is a button that just says e. It's right above division, but it doesn't give you the exponent. I would encourage you to use the one above. Sorry, I forgot a 0 there. Let me just move my decimal. Here, I'll just write it again. There's a 0 after the decimal there. There we go. So 0.0498. Okay, we're going to use this log to solve some equations now. I'm going to go 5. I'm going to try this again. I looked at the wrong problem. I want to do a different one. We're going to go 5 ln of 6x is equal to 8. So I want to solve this equation. I want to figure out what x is. What should happen first? I would divide the 5 away. So I want to isolate the ln. Okay, so I divided the 5 away. Now the ln is isolated. ln is a type of log, remember that. So we have a log. How do we get rid of a log? We exponentiate. So how do we get rid of an ln? We exponentiate. What base shall we use? 6 is not the base number I'm trying to get rid of. So someone probably said, I think I heard it, e. ln is log base e, remember? From up above, that's what ln means, log base e. So the base is e, even though we don't write it. And I'm trying to get rid of the log base e, the ln. So I would exponentiate with an e. So e to the ln of 6x is equal to e to the 8/5. What does that e do? Well, it cancels out the ln on the left side. So we get just 6x on the left side. On the right side, it doesn't cancel, so we actually have e to the 8/5. I'm not going to plug that into the calculator just yet. I'm going to pull out the calculator at the very end when I already have x by itself. What will we have to do to finish off the problem? So we'll divide it by 6. So pull out the calculator, do e to the 8/5, and divide that by 6. .8255. Okay, let's take a look at this inequality. We have the natural log of 2x minus 3 cubed is greater than 6. The first thing that I would highly recommend doing is moving that exponent. We have an exponent inside of a log. If we have an exponent inside of a log, can't we take that exponent, move it in front as a coefficient? So when we do that, we have 3 times the natural log of 2x minus 3. And that's greater than 6. Then, what can I do with the 3? I want to get rid of it, so I would divide by the 3. So I end up with the natural log of 2x minus 3 is greater than 2. So now the natural log is isolated. I'm ready to exponentiate. I will use a base of e because it's a natural log. E to the ln cancels out on the left side, leaving us with 2x minus 3 is greater than e squared. Don't pull out the calculator yet. I'll save that for last. So then I would add 3 to both sides. So 2x is greater than e squared plus 3, and then we divide by 2. So on your calculator, find out what e squared plus 3 divided by 2 is. I get x is greater than 5.1945. If you didn't get that number, make sure that like you maybe put parentheses around your numerator. You can do parentheses e squared plus 3, close the parentheses, then divide by 2. But you should get 5.1945. This is a logarithmic equation, or inequality rather. And logs have restricted domains. Are we going to have to restrict this answer? Well, remember what we did with domains on other logarithmic equations. You would look at what you're taking the log of. You're taking the log of 2x minus 3. What do we know about 2x minus 3? It has to be what? This was on the last quiz, and some people didn't remember what to do. But you would say that that domain, or that 2x minus 3 has to be greater than 0. So now you can solve that. So we know that x has to be greater than 3/2, or 1/2. So if I come down here to my answer, I said that x had to be greater than 5.1945. Is all of that okay in the domain? Yep, it is. So that's your answer. We don't have to restrict it. So those two problems are logarithmic equations or inequalities. We also need to look at exponential equations or inequalities that use e. So that's what we'll do next. So 3e to the negative 2x plus 4 is equal to 10. We need to solve this. It is exponential. So it is important that we isolate the exponential piece of this. So it means first thing I would do is subtract 4. Then I would need to divide away the 3. At that point, we have e to the negative 2x is equal to 2. To solve this, it is exponential, so what are we going to do? Yeah, so we're going to log it. And I want to get rid of, I'd like to get rid of the base number of e. So if I'm going to log with the base of e, that's actually ln. So I just write ln in front of the left side and write ln in front of the right side. And when I do that, on the left side, the ln will cancel out the e, and we're left with negative 2x. And on the right side, I have ln of 2. Then to finish that, divide both sides by negative 2. Can you cancel out the 2 on that fraction? No, the top one's in an ln. That's not really 2. It's the natural log of 2 divided by negative 2. Plug this into the calculator. More or less. So we get about negative 0.3466. So that's how you would handle the exponential equations. There is one other piece of this section that's kind of an application piece and a little bit about why do we care about E? And I mentioned already that it's used in the financial world some. If we think back to the beginning of the unit, we talked a little bit about compound interest. So interest, you might get interest at the end of the year. It might just be compounded annually, but it might be compounded quarterly or monthly or weekly or daily. Is it in your benefit to have interest compounded more frequently or less frequently? If it's your savings account, if it's your money, you'd want it more frequently, right? The more frequent it happens, the more often you build, the more you build interest on your own interest. So what happens if we tried to compound your interest even more rapidly than once a day? Could we go once an hour? Could we go once a minute, once a second? What's the shortest, or what's the most it could happen? Well, the most it could happen is like an infinite amount of times in a year. We actually have a name for that, and it actually is a real thing. It's called continuously compounded interest, and that's an application of this number E. So let me jump over, change directions here a little bit. We'll give the equation. This is continuously compounded interest. You might, in theory, think that if you get interest compounded an infinite number of times in a year, you're going to have an infinite amount of money. That's not true. It's not going to be much more advantageous to you than like daily, but it is a little bit better. Here's how you calculate your balance. You take your principal times the number E, and E is raised to the exponent of R times T. Now, I'm not going to define any of those variables because I've already defined all of them. It's the same variables from our other compound interest or our other interest problems. R is rate, T is time, P is principal. And E is not a variable, E is a number. So let's go ahead and actually try this. And let's compare it to a different compound problem, just so we can kind of see the difference. Let's say we're depositing $20,000. Let's say we're going to, I don't know what, let's choose a rate. Oh, I'm going to use like 3%. Now that's really high for a savings account. You're not going to find a savings account that high, but we'll go ahead and use it anyway. 3% APR. I want to find out what our balance would be after, let's say, 10 years in a couple of different scenarios. One, if it's compounded monthly. Two, if it's compounded daily. And three, if it's compounded continuously. So the formula that I've given you up here, will I get to use that formula in each of those three scenarios? No, that's only going to be used in the third scenario. That equation with the E is only if it's continuously compound interest. Our first two scenarios are monthly and daily, less frequently. So we've done that before. That was the beginning of the chapter. You would take your principal times 1 plus your rate, but change it to a decimal, 0.03, divided by how many times you're getting interest in a year. So if we're going monthly, that's 12 times. There's 12 months in a year. You're only getting a 1/12 of the interest each month. But then you're getting interest 12 times a year for 10 years. That's 120 total interest payments. So you take the 12 times a year for 12 years, multiply those together, that's your exponent. And let's go ahead and calculate what this is. Use the calculator. This material, like these first couple questions were quizzed on your, or were assessed on your quiz already. We've already assessed on this, so hopefully you're okay with these first couple. We get $26,987.07. So you made just shy of $7,000 in interest in those 10 years. Let's look at the same numbers now, but daily. So you're getting interest more frequently, still the same percent of interest, still the same principal, still the same length of investment. Let's find out the difference. We're going to go ahead and use 365 days for the year. This being a leap year, we actually have 366, but just use 365 for this. And then for 10 years, this time we're going to get $26,996.84. It made us a little bit more money. Nothing different on our part. It's just compounding more frequently made a little difference. So any guesses before we do this next one? Any guesses what might happen if we compound it continuously? You think it's going to hit 27,000? Here's some no's. Anybody think so? Yes. Yeah, maybe. Let's go ahead and find out. $20,000 times E raised to the power of your exponent, so 0.03 times the number of years, 10. We get $26,997.18. Was it the best of the three options? Yeah, but it wasn't a big difference over daily. 34 cents or so. But we'll take it. All right, your question. Okay, so that concludes our notes over this section.